Hello, we are Team 1. Today, we'll discuss the challenges encountered in the construction of the glass hull designed by Raffaele Vignoli to showcase lightness and transparency and the structural solutions adopted to overcome these challenges. Constructing a building entirely clad in glass presented significant difficulties in resisting strong lateral forces, including wind force and earthquakes, while maintaining its original shape. To address these issues, we examined three major structures: the cable truss for the glass facade, the rib-like large roof structure, and the main columns. This week, we'll discuss the process of constructing this enormous glass hull, focusing on temporary structures and components used to counteract horizontal forces before the hull was completed, as well as an overview on the entire construction process. The construction of the conference hall steel frame began during the top-down phase, marking the commencement of construction at the top part of the building. With the building height at 57.5 meters, the bend stage was necessary to support the steel roof and facilitate the construction of the upper parts of the building using a traveler crane. The bend stage also served as a temporary storage area for equipment during steelwork and to prevent buckling of the wall steel. It was crucially designed to be robust enough to handle the horizontal forces that occurred during the installation of the main columns and wall steel. Initially, beams at the base of the bend stage were anchored using chemical anchors and secured with non-string mortar to solidly secure the base of the bends. Then horizontal beams were installed to support the upper bend and the axial force of the traveler crane. The following describes the two structures constructed using the bend stage, the main columns, and wall steel. The main columns not only supported the axial load from the roof steel, but also transferred the horizontal forces from the roof to the conference hall across floors 4 to 7. The main column started at the core column, height of 7.5 meters below ground, and were connected on site by welding divided into 17 sections. When constructing the main columns, the lower parts used tie rows to resist horizontal forces and were then connected to the bend stage to further resist horizontal loads. Sections from 11 to 17 were built to resist the axial load from the roof and transferred horizontal forces to the conference hall using concrete with a strength of 80 MPa. In contrast, sections from 1 to 10 used concrete with a strength of 30 MPa. The wall steel served as a temporary structure needed for subsequent wall cable truss and glass frame construction. The wall steel was connected in the shorter direction to bend stage and wire frames, providing support for horizontal forces. The construction of the roof steel frame is divided into three parts: the saddle-shaped part, the rib part between the shoulder pipe, and tip parts, also known as the shoulder pipes. Here, the bend stage previously used for the construction and support of columns and wall steel continues to be utilized. First, the saddle-shaped part is assembled from 13 pieces made of fire-resistant steel weighing a total of 60 tons. This assembly was carried out on site using a traveler crane positioned on the upper bend. Second, the assembly of the ribs and the shoulder pipes proceeded in the following order. 1. Supports were installed on the upper bend. 2. A shoulder pipe block was assembled on the supports. 3. Each shoulder pipe block had 3 joints connecting one rib at a time. This assembly process utilized a hydraulic traveler crane mounted on the upper bend. During this construction process, a shape management system was implemented to prevent and manage deformations caused by wind load and thermal expansion. This system, leveraging light deflection and ranging technology, abbreviated as LiDAR, measures three-dimensional displacements. Monmouth's total station was used in this system. Now that the roof construction is complete, not only the main columns, but also the top 44 bends are supporting the load of the roof. To remove the bends and transfer the entire load to the two main columns, HT rod tension introduction and jack down were utilized. HT rods can be seen among bundles of cables on the roof. These HT rods consist of three parts: the tip suspension rod, the central suspension rod, and the bottom tie rod. The roof steel frame, due to moment forces, has the tip part elevated while the center part is sagging. At this point, hydraulic jacks positioned at the 1st and the 10th ribs apply tension to the rods, leveling the inclined roof. The tension applied is monitored through gauges attached to the rods, and this process is known as HT rod tension introduction. Once tension is applied to all rods, the jack-down process begins. A total of 20 hydraulic jacks located at top bends control the displacement in 1 mm increments, gradually transferring a total load of 3,000 kN from the bends to two main columns and the shoulder pipes. After completing the jack-down method, the feared tilting of the roof did not occur, and the central displacement of the roof was measured at 341 mm, analyzed at 345 mm, while the stretching of the shoulder pipes was 78 mm, analyzed at 76 mm. This result, corresponding to an error of only 2%, was a remarkably successful operation. While the vent structure and the stage for the frame construction in place to absorb horizontal forces, the installation of the external glass frame could commence. Since the vent structure was only erected up to 42 meters, the installation of the overall external frame and glass cable truss was conducted up to 25 meters. The assembly and welding of the steel frame were repeated, and the mullion installation was conducted from 0 meters to 20 meters in one go. As explained last week, horizontal forces are transferred from the steel frame to cable truss, and here is the construction process of the cable truss. The upper and lower cables are pre-tensioned using the tension jack of the triangular tension plate at the lower part. Once the cable tension reaches the specified value, the tension plate is fixed to the lower work plate. The cable is connected to the vertical members of the cable truss, which serves as a core using cable grips and saddles. During the introduction of pre-tension, the cable slides into position through the cable grips. At this point, the positive compression cable is positioned outside the core, and the negative compression cable grip is positioned inside the core. After introducing the pre-tension, the stoppers between the cable grips and saddles are removed to induce sliding, guiding the cable to the stable position. This cable truss not only supports the glass facade, but also helps prevent the roof structure supported by two main columns from toppling over. This week, Team 1 explored the overall construction process of the glass hull, focusing on bend stage, roof, HT rod tension introduction and jack down, and cable truss. We discussed how these structures interlock and support each other, ensuring stability during the construction period, particularly in resisting horizontal forces and loads. Next week, we'll delve into structures and construction processes used to mitigate internal and external vibration in the concert hall. This was Team 1. Thank you for listening.